Okay, welcome to the lecture here. We're going to get lecturing on chapter 1. Again, a reminder that the notes are up there on Canvas if you need them. So right there, maybe in the middle of Canvas. And again, a reminder, please put here in the chat box. And again, every time we log into lecture or lab, just please put here at the beginning and we'll use that for roll. Yeah. So again, as I mentioned, the notes there are found on Canvas for all the chapters. I think they're all up there already. So again, if you want to print them out, use them or use them as a PDF and however on a tablet or whatever you like to do with them, birdcage liner, whatever you want to do, you could use them. But we will get started here, I think. Just get a couple things out of my way, I think. Okay, so we're going to be covering chapter 1, and as we sort of talked about the other day, our textbook is a little bit different than sort of a normal textbook in terms of how it is sort of structured. We do start with atoms first, so as I mentioned last time, we're going to start with really getting right in this first chapter about the experiments that led to the structure of the atom, the structure of the atom, protons, electrons, neutrons, all that kind of stuff. Then we continue on in the next chapter into some electrons, electron configuration, all that kind of stuff. So as I mentioned before, I believe in our textbook, and by the way, that's an old cover, so I think our new one is a red color, I think. But our in this textbook, I believe like all that kind of significant figures, conversions, and all that kind of stuff that you normally find in like the first chapter, measurements. I think it's in like a pre-chapter in this book. So you are responsible for that stuff. Again, they sort of assume that you have that sort of knowledge coming in. So you might want to review it. As I mentioned as well, I think in a couple weeks, we'll have a lab where we'll kind of officially sort of talk about that stuff, significant figures, conversions, density, just to make sure, again, everybody's sort of on the same page with that. But officially, I don't believe a chapter in your book is sort of that pre-chapter. And you want to make sure that you do sort of cover that stuff. And we will, again, officially sort of cover it. All right, then let's get started then on chapter 1. And maybe things will move. There we go. All right. So really, when we talk about sort of chemistry, really chemistry is all about sort of really matter. We sort of look at matter a lot in chemistry. We look at how it changes, the different states of it, what's happening as it goes from sort of one state to the next. Oftentimes we try to think about sort of the macroscopic sort of level, the big picture of what's going on. But we also try to focus in on, obviously, on the sort of microscopic picture of what's going on, especially when we deal with atoms, molecules. So, for example, obviously in a chemical reaction, as you may know, really the only thing that's happening is pretty much we're breaking apart all the bonds on the reactant side of the equation, and they're basically reassembling on the product side. And as they reassemble, they do form new molecules, perhaps on the product side. So a lot of what we look at is sort of what's happening with all that kind of stuff. When we think about, when we think about matter, again, as we'll see and sort of talk about, matter really is pretty much anything that sort of occupies space, has mass. So pretty much everything around us is just let some people in here. There we go. All around us, and it can be in different states. So a lot of times when we do talk about matter, we talk about sort of the 3 states of matter, things like solid, liquid, and gas. And a lot of what we sort of deal with, like I mentioned, sort of in chemistry, is really what's happening to different substances. A lot of times as they sort of transition from one of these states to another. As you may know, right, if we're in sort of the solid state, that usually means things are packed in pretty tight to one another. There's not a lot of room for movement, right? That's why we think about things in the solid state as being rigid, very hard to sort of change the composition of it or change the structure of it. When we get to our liquid part, we still have everybody packed in relatively sort of tight to each other, but there definitely is a lot more room for movement. And that's why we oftentimes think about liquids as being fluid, right? They're able to sort of pass each other, the atoms, the molecules that are basically involved. And that's different than when we get all the way down, obviously, to great belly button, draw this box there, gas stage, where everybody is pretty much broken apart from one another. They're flying around, they're causing collisions as those gas molecules are flying around, and which obviously causes pressure that we associate with it. We definitely will hit that when we get to the gas chapter. And a lot of what we deal with is sometimes these transitions. So just a reminder, as we go from solid to liquid, that is the process of melting. We go back from liquid to solid. That's the process of freezing. Going from liquid to gas is evaporation, or vaporization is sometimes referred to. Heading from gas back to liquid is that process of condensation. We also, as you might remember, can go from solid and actually skip that middle section there, the liquid, and go right to our gas. And that's the process known as sublimation. We also could go the opposite way, which is going from gas all the way back to solid. And that's the process where we kind of skip liquid going in the backwards direction. And that's what's known as deposition. We also think about things as these sort of transitions occur, what is happening, what is actually happening in terms of things like energy. Although we don't talk an enormous amount about energy in here, very little. You actually talk more about it in 200B when you take it. They kind of moved all that energy conversation to that class. But, for example, as we go from solid to liquid to gas and kind of moving in terms of those stages, in terms of heat and energy does need to be sort of absorbed in this process to do that. And you might remember that when we talk about things being sort of heat and energy being absorbed, that is what's sometimes referred to as a endothermic process. So you can just think about a very simple example of, you have an ice cube. Obviously, you take the ice cube out of the freezer, put it on the table, for example. It's going to pick up all that heat and energy from the surroundings. It's going to start to melt, and you'll have liquid water. Then perhaps, you take that liquid water, you put it up there on the stove, and you start boiling it because, you're going to make some pasta. Seems good. It's dinner time. And you make that pasta, and, you boil that water and get a lot of steam that happens. And again, that's our evaporation happening, putting all that heat and energy in. Opposite to that is sort of the opposite process where we go, say, from gas back to liquid, back to solid. In order to do that, really heat and energy needs to be released. And when we release heat and energy, that's a process which is sort of referred to as being endothermic. And just sort of logically think about, if we start with, say, the gas phase, and we have all these gas molecules that are basically flying around. And if we remove heat and energy, as they come to each other, they're no longer going to have enough energy really to kind of bounce off each other. They're going to kind of stick a little bit. And as they stick, they'll sort of drop into the liquid phase. Obviously, if you continue to sort of take the heat and energy out, you would go from the liquid phase to the solid phase. Again, we could use sort of our ice as an example of that. If you have your liquid water, right, how we make ice cubes is we put liquid water, right, and then basically put it in the freezer. By putting it in the freezer, it's removing all that heat and energy, allowing all those guys basically to come together into the solid phase. And we do see, obviously, ice form, which is the solid version of water. Any questions on that there? Now, a reminder that some things you maybe know, maybe don't know, but just to make sure we're sort of on the same page in terms of things. When we talk about melting and freezing, these things do occur at the same temperature. So these really do occur at the same temperature. So, for example, water is 0 degrees Celsius where that occurs. And it really depends on at 0 degrees Celsius, for example, what you're doing. If you're continuously putting heat and energy in, you'll head towards melting and liquid state. If you're sort of removing heat and energy at 0 degrees Celsius, you'll go towards the solid state. So, for example, that's sometimes referred to as the freezing point or melting point of a substance. And again, these things do occur at the exact same temperature. Same deal over here. You know, when we talk about sort of these transitions here, they also occur at the same temperature as well. And again, pretty much the same idea. It really depends at that temperature. So, for example, water, when we talk about water, its normal boiling point is 100 degrees Celsius, which means when you're exactly at 100 degrees Celsius, you actually have sort of both phases happening at the same time. So, you got a little bit of, say, liquid water, a little bit of steam happening. And again, it's not really till you get a little bit above 100 degrees water, for example, that you get really steam or the gas phase, not to get a little bit below 100 degrees Celsius that you do get into the liquid phase. But again, it just really determines on what you're doing as to whether you are basically putting more energy in or putting more energy out to do that. So this again, usually we sort of talk about this point as being the boiling point of a solution or a substance, is where that transition occurs between our liquid and our gas. Now, in terms of energy, since we're talking a little bit about energy here, and again, we don't talk a tremendous amount in this class, but believe it or not, when we're at, say, something like 0 degrees Celsius for like water, which is his normal melting and freezing point, there's actually a certain amount of energy that's required to simply do either one of two processes, either take it from solid to liquid or liquid back to solid. And again, not change the temperature because that's where it happens at 0 degrees Celsius. And that's what is sometimes referred to as the delta H of fusion. And that's sometimes referred to delta H is the heat of fusion. And it's really delta H is what's known as enthalpy. It's a fancy symbol for heat, basically, of what's going on. And also at 100 degrees Celsius, you know, for example, that's where we have that transition of liquid to gas, or really gas back to liquid. And that is where we have our delta H, what is sometimes referred to vaporization or heat of vaporization. And again, it just means there's a certain amount of energy that's required really to simply not change the temperature, but take a substance at, say, 0 degrees Celsius from solid to liquid at 0 degrees Celsius and do nothing other than actually just change the state of it. As you might guess, it actually does take a lot more energy to do this transition, going from, say, liquid to gas or gas back to liquid, than it does the solid to liquid or liquid to solid. Again, in terms of going from solid to liquid, if you just kind of look at the pictures, in solid, everybody's really tight to each other. Liquid, they're still fairly tight to each other. So it doesn't take a lot of energy to kind of break them apart a little bit. But when we go from that transition of liquid to gas, we're going from a place where they're pretty close to each other to a place where they've completely separated from one another, which obviously would take a lot of energy to do that. So it's always a lot more energy to do that transition, going in both directions, going from liquid to gas or gas to liquid, than it is going from solid to liquid or liquid to solid. And just sort of a reference point, if you want, for water, the heat of fusion is something like 333 joules per gram. The heat of vaporization for water is about 20 to 60 joules per gram. So you can see doing that transition from liquid to gas is about, I don't know, was that 7 times more energy required to do that? And again, it's because you're really breaking people apart from each other. Last little bit about our little preview of energy, I guess, or probably all the energy we're going to talk about. When we talk about things that are exothermic, if you ever see values, and usually when we talk about sort of energy and stuff like that, it really is this delta H value that's oftentimes how energy is displayed sort of in chemistry. And usually exothermic things have a negative value in terms of energy, and endothermic things have a positive value. Any questions on any of those things there? Okay. So as I mentioned before, matter again is really anything that sort of, has mass and occupies space. So pretty much like I talked about, anything will pretty much meet that definition. But really matter, the basic sort of unit of matter is really atoms. Atoms are the basic sort of representation of all the elements that we see sort of on the periodic table, as we'll talk about definitely in this chapter. And as you probably know, right, atoms basically have protons, electrons, and neutrons, right? Most of them that make that up. And when we do combo 2 or more atoms together, that is what makes a molecule. So a molecule is the simple sort of definition of you put 2 or more atoms together. Those could be 2 or more atoms that are from the same element. They could be 2 or more atoms that are from different elements. But the basic definition of a molecule is just that. Simply, we have joined together through probably bonding or something of that nature, 2 atoms that have come together. Now, there are molecules that are elements. So there are certain elements that how they naturally come are as molecules. So H2, which is hydrogen gas, oxygen gas, nitrogen, fluorine, chlorine, bromine, and iodide, they all come naturally as basically 2s. So these are what are sometimes referred to as diatomic molecules. Now, they're diatomic molecules. They are molecules because basically something like hydrogen is 2 hydrogen atoms together. Something like oxygen is basically 2 oxygen atoms that have been bound together. Nitrogen is 2 nitrogen atoms that is basically bound together. And they're all molecules because basically they meet the basic definition of a molecule. There's basically one atom attached to another atom. So that makes them a molecule. But they are basically still elements because they are only made up of the same element. So when we talk about H2, it's made up basically of 2 hydrogens, which is the same element. Oxygen, same idea. It's made up basically of 2 oxygens, so it's the same element, and nitrogen. So molecules can be elements. We could also have something like water here, as the little picture here is. H2O, which is basically this. And water is a molecule because it does meet the definition of there's 1 atom there, 2 atoms, and 3 atoms. So that definitely is 2 or more atoms that are basically bonded together. And sometimes people get confused by another terminology that we sometimes hear, which is compound. What is the difference perhaps of a compound and a molecule? So there is a difference. When we talk about a compound, the definition is basically atoms of 2 or more elements together. So in order for something really to be a compound, it does need to have atoms of 2 or more different elements. So what that means is water is a molecule. Water would also be a compound because it has the elements of oxygen and hydrogen involved. Something like carbon dioxide would also be a molecule because it basically is the combination of 2 or more atoms that are together. But it is also a compound as well because it's a carbon element involved, an oxygen element involved as well. Now, water and CO2 would not be considered an element because it is made up, obviously, of more than one type of element in that particular case. So molecules can be both elements, molecules can be compounds, but compounds cannot be elements because the definition of a compound is you need to have 2 or more different elements that are basically involved. Any questions on that there? So when we do sort of represent, for example, molecules and things of that nature, we do write them as subscripts, right? In the forma, we use the chemical symbols, and we use subscripts to indicate how many of each of the atoms we have. So if we had something like our H2O we were just talking about, the subscript, which is the small number, always goes to the guy to the left. And if there's nothing written there, it is assumed to be 1. So basically, this tells us that we have 2 atoms of hydrogen for every 1 atom of oxygen. We obviously could do that for something like our CO2. Again, here, 1 carbon for every 2 atoms of oxygen in that case. Same thing here. This basically tells us we have 2 oxygen atoms, which obviously this is oxygen atom number 1 here and number 2 in that particular case. Now, a chemical reaction, as I mentioned a little bit earlier, the basic really definition of a chemical reaction is a chemical change that's going on. And the important thing to remember in a sort of traditional chemical reaction, really the only thing that is sort of occurring is we have one side of the reaction, which are known as the reactants. So for example, the left-hand side of the arrow are what are known as reactants. And those are really your starting material in a chemical reaction. On the other side, we have our products, which is your substances that are produced as a result, obviously, of the chemical reaction. But what's important when we think about a chemical reaction is we never lose elements along the way. So essentially, as I mentioned, what is essentially happening is we're basically just breaking everybody apart, breaking all the bonds. And basically the same elements that we started with will rearrange on the product side and make some new bonds over here. And obviously make some new substances and stuff like that. Now, water, which is a compound, as we see here, can go through a chemical change, which is basically what we're doing here. The electrolysis of water, basically run an electrical current over water. You will produce hydrogen gas and oxygen gas in this particular case. And these are elements, right, on this side. So that's H2 and O2 on this side. And we do see that that can happen. So through a chemical reaction or a chemical change, we actually can break down compounds into smaller parts, which are really the elements. But once we get to the elements, we really can't go any further back. That is basically as far back as we could take everything, is to basically breaking them back down into their elements. Any questions on that? Okay. So now we kind of had a little overview of sort of chemistry, and obviously some of these topics we will definitely go into more detail in later chapters. But let's talk a little bit about sort of the scientific method and the process that's sometimes used. And really, the scientific method involves several steps, and really most of the steps begin with an observation. Most things in life begin with an observation, maybe a good observation, a bad observation, maybe things you don't want to remember you saw anymore. But observations, right, is what this basically built upon the idea of sort of the scientific method. Somebody does observe something that's happening, and they try to maybe figure out, why does that happen? So what usually will happen is we'll have some type of observation, and again, they people will try to come up with sort of a tentative explanation of sort of what they observed. Most of the time, especially sort of in the science area, these hypotheses are usually some testable type hypothesis. Usually, you could do some type of experiment to kind of figure out, what's going on, why things are going on. That usually leads to experiments, and this is the part where it can lead into maybe perhaps a vicious sort of circle, because usually when you do experiments, you observe things, and perhaps you observe things you didn't expect to observe or you didn't see maybe the first time. That leads to more questions. That leads to you maybe sort of revising your hypothesis, retesting, and so forth. So it can be a circle sort of event, as you can see here by the arrows. Again, we have our observations, we come up with a tentative testable explanation, run some experiments, and we kind of circle back around here, and we hit more observations, which leads more to more and more sort of studying. At some point, though, it can get itself into some type of theory that basically could come about from these experimentations. A theory is sort of a explanation that sort of summarizes what happens. Is it correct maybe in all aspects? It's not, probably, in a lot of cases. It can be sort of modified. So for example, there's certain theories that we'll talk about. One in this chapter, for example, something like Dalton's atomic theory. Some parts of it is sort of correct, some parts of it is not sort of correct. Bohr's model or theory of the atom, hydrogen atom, works really great for hydrogen. Doesn't work so great if you move to things that are not hydrogen and stuff like that. So, theories, for example, sort of explain what's happening. They're maybe not set in stone. They can be sort of revised and stuff like that. And that's different than perhaps something like a law. A law is, something that's sort of been proven to always sort of happen no matter what the situation is. You always see, for example, conservation of energy, as we were just talking about. So if we start a reaction, for example, with four carbons, we should end the reaction with four carbons as well. It may be in a different form on the other side, but we have that conservation sort of a mass that we don't really lose anything along the way. We keep what we start with, we end with what we start with. We don't do anything like that. In terms of energy as well, for example, conservation of energy, we don't lose, we don't create energy. Energy can be moved from sort of one part to the next. Usually, when we talk about energy, we talk about it as something sort of perhaps losing energy. But if something loses energy, there's something else that will pretty much gain all that energy. So there's sort of a balance that always happens. And again, that's sort of the law of conservation of energy, always happens that way. Usually not sort of reviewable, not sort of modified or anything like that. And again, that's sort of a difference between a theory or a model. Again, it's a pretty good guess as to what's going on, but it can be sort of revised if it's sort of more of a theory or a model. Again, a hypothesis is usually some type of tentative explanation. And again, in most cases, we really want to make some type of hypothesis, that really can be tested. So you can make sure that, it's something that you can sort of put to the test and see if perhaps your prediction is correct. Any questions on the scientific method there? Okay, so we're going to now sort of get into pretty shortly here. We're going to talk really about the atom. We're going to kind of move into, in a few slides down the road here, talking really about the atom. And we're going to talk about some experiments that were important in understanding sort of the structure of the atom, the modern atom that we sort of think about, obviously when we think about what the atom is or how it looks. And as we go through it, I'll sort of summarize as we get to the end, and as we're going through, like, hey, this is something that you should know, as we kind of go through it. So we're going to talk about some experiments. We'll talk about what experiments, obviously, you should know, and those type of things as we kind of go through it. All right, so let's talk about then sort of the early idea of really an atom. And, there's a lot of people sort of involved in early experiments, even way back to sort of Greek philosophers where, they thought they came up with this idea of atomos as sort of an early running of, obviously, if we get rid of the last part there, of atoms, basically. And they come up with, what it might be, these sort of indestructible sort of properties and substances that, basically will not, be destroyed or able to be destroyed. A lot of years past that, a lot of people did a lot of work. Robert Boyle, for example, is sort of considered the first chemist for a lot of quantitative experiments. Quantitative means measurements, as opposed to qualitative, which are more observation type of perhaps experiments and stuff like that. You may also recognize Robert Boyle from like Boyle's Law, right? Which we'll obviously see when we get to the gas chapter. So we'll see that again. And again, we were just talking about sort of laws and just to touch upon some of these laws. And again, we may see them in some future chapters as well. One important law is obviously, as I mentioned, that conservation of mass. So we never sort of create nor destroy mass. And again, pretty much what that means is, for the most part, if we think about sort of a chemical reaction, if we started with, say, 4 carbons on this side, 2 hydrogens, in whatever form they may be, when we get to the product side, which is what's made at the end, we also should have 4 carbons, 2 hydrogens. Obviously, the mass of 4 carbons on the left-hand side would equal the mass of the 4 carbons on the right-hand side, even if they may be in different compounds on each side. Same idea. We started with the mass, for example, of 2 hydrogens on the left. We ended with the mass of 2 hydrogens on the right. So since in basic chemical reactions, really all we're doing is basically rearranging everybody. So we're breaking everybody apart, we're rearranging, and that means we should end up with the same elements. And since they all have the same masses on both sides of the arrow, if you want to think about it that way, we should really end up with the same overall mass when it's all said and done. Another important sort of relationship is one that's known as the law of definite proportion. And that basically means that when we have a compound, it always contains really the exact same proportions of elements by mass. So basically, what does that mean? It means, for example, if you took something, say, like water, which is basically H2O, it basically has 2 hydrogen atoms, and it basically has 1 oxygen atom. And basically what that means by mass is for every 2 hydrogen atoms, each one's about 1 gram. There's about 2 grams, a little bit more, of hydrogen for every 16 grams of oxygen. No matter where you find your water, no matter what it is bottled in, may just cost more depending on what bottle it is in. But, ultimately, if you're talking about the water part of it, it is still H2O no matter where you get it. And really, that's the same idea as saying basically for every water, there's 1 gram of hydrogen for every 8 grams of oxygen that's there. And again, no matter where you go, no matter what you do, it's always going to be that if you're talking about really something like water. So again, we always have these compounds that come out in these exact sort of ratios or proportions based on mass, based on the elements that are present. The third sort of important law is the one that was done by Dalton. That's a law of multiple proportions. And basically, what he said was, for the most part, when elements come together to form compounds, they basically do so in ratios that the second element will always combine with 1 gram of the first element. And basically, what he's saying is they will come together as kind of whole numbers, which means, if you take a carbon atom, for example, and an oxygen atom, and you put them together, it comes together in this case as 1 carbon atom and 1 oxygen atom, sort of a 1-to-1 ratio, whole number ratio. You could put together a carbon and 2 oxygen atoms, which gives you a 1-to-2 ratio of how they come together. But you really will never find like a half a carbon atom and like a half of oxygen atom coming together. So they'll never come together in sort of a half ratio. You got to have that whole sort of atom coming together in each of those cases. And when they do come together, they do come together in that whole number ratio. And that's why when we write things, like chemical formulas, for example, and we write those subscripts like H2O, these numbers on the bottom should really always be whole numbers. You will never again, get like a third of an atom happening or a half an atom coming together. So they're always going to kind of come together in these whole number ratios. And they will always come together really in sort of simplest whole number ratios. And that's, for example, why if we look at like an ionic compound, like say sodium chloride will always come together in a 1-to-1 ratio, which is the simplest way that they could come together. All ionic compounds will come together in the simplest way. And as you may be familiar with, right, sodium has a +1 charge, chloride has a -1 charge. And this is an ionic compound. Opposites attract, right? Much like in life. If you have two negative people, they really don't want to be around each other. Two positive people, probably not around each other. But hey, you get a positive and a negative person, kind of balance each other out. So same idea here in chemistry, right? They balance, they're attracted to each other. And the simplest way they could come together, again, is 1 sodium and 2 chlorides. You could even go, hey, if I put 2 sodiums together, I would need 2 chlorides, and they would be balanced. But this is not the way that they would come together based on a law like this. They would come together in the simplest whole number ratio to get them there. And again, that's a good thing to keep in mind, especially when we get into naming again and writing formulas. Sometimes people do write crazy formulas because they see charges. But really, ionic compounds, which is a metal and a non-metal, always come together in the simplest whole number ratio that's present. Any questions on that there? All right, so now we're going to get into some important parts of experiments and ideas that led really to the formation of the atom and how we sort of think about it today. The first really big sort of step was done by a guy named Dalton. He wasn't a very good lecturer. He was very good at math and science. He kept the weather report every day. He woke up, wrote what the weather was like. Oddly, never married. But he did go bowling on Thursdays. That's always an important piece of information right there. Remember when I asked that, it is Thursday. It's not like, Friday, cosmic Saturday, 2-for-1 Wednesday. He will be going bowling on Thursday. I know you might be thinking, probably not going to ask that question. So don't be surprised when the question is asked, just so you know, it will be asked. But really, besides going bowling on Thursday, which is really important, one of the important things that he really did do was come up with really sort of a precise definition of sort of what we call atoms. It's what's sort of referred to as Dalton's atomic theory. It is a theory. So as we just talked about, perhaps not all aspects of it is correct. We're going to go through the different parts of it. And again, you do need to know the different parts of his atomic theory. So let's take a look at some of it. First part of it was that each element is made up of these tiny particles called atoms. They're sort of indestructible, if you will. And as we will later see, maybe that's not so true that they're indestructible. They're not necessarily indestructible. There's things that are like, for example, nuclear reactions, which actually can change an element from one element to the next. So they're not necessarily indestructible. So that's one sort of part that's not 100% correct. Another part of his theory was that atoms of a given element are identical, and atoms of different elements are different in some fundamental way. So although part of this is correct, and obviously atoms of different elements do have some type of fundamental difference, the part of this theory which is not necessarily correct is sort of this first part of it, which is atoms of a given element are identical to each other. So basically what that means is like, hey, if I have a carbon atom, no matter what the situation is, they're all going to pretty much be the exact same. And they're actually not, again, the presence of something like isotopes, which we'll talk a little bit more later on in this chapter. Isotopes are really the sort of same element, but they have different numbers of neutrons, for example. And that right there tells you that although they're both, for example, carbons, you could have something like carbon 64, have something like carbon 67. Difference between these two, they're both carbon, but they do have different numbers of, say, neutrons, for example. And obviously that doesn't mean that they're going to be identical, because if you come across a carbon 64 atom and a carbon 67 atom, they would obviously have those different numbers of neutrons, and that means that they're not perfectly identical to each other. Obviously the other part is okay in terms of, different elements do have atoms that are different to each other. So those two main things from Dalton's atomic theory is not necessarily 100% correct. Again, they're not necessarily indestructible, and they can have atoms of the same element that are not identical to each other. Again, the presence of something like isotopes, as we just talked about, basically kind of proves that. Another important part of his theory was that when we basically, have a chemical reaction or combine compounds to form compounds, they are different elements that come together. And again, they always do come together, as we sort of talked about a little bit earlier, in these simple sort of ratios. And again, you could get different sort of compounds depending on sort of the combination. So if you think about, like we were just talking about, if you take a carbon and an oxygen atom, only one of them, you get something like carbon monoxide. Take a carbon and two oxygen atoms, you get something like carbon dioxide. Again, they have very different properties, but they're still ultimately made up of the same two elements. Same if you did something like NO2, which is nitrogen and oxygen, you could take N2O, which is still nitrogen and oxygen. And again, these guys, although they are made up of really the same elements, they do have some different properties associated with them. The last part of sort of his atomic theory was that chemical reactions, as we also touched upon, are really involve only the breaking of bonds, sort of the rearranging of those bonds. Again, we don't lose any elements along the way in a chemical reaction. And whatever we started with, as we talked about, is sort of in terms of elements, what we'll end with. Atoms themselves are not changed in a chemical reaction. In a nuclear reaction, which we don't talk about in this class, you talk about in Chem 200B. In nuclear reactions, they are definitely changed. You actually change one element to another because we're changing protons, electrons, and neutrons. So those are the main parts of Dalton's atomic theory. You do need to know them. You do need to know sort of, which parts of it is maybe not so correct anymore. Any questions on that? And this question will sort of summarize those differences. So in this case, we're looking at which of the following statements regarding as atomic theory is still believed to be true. So let's just go through them. We have elements are made up of these tiny particles called atoms. So that is still good. All atoms of a given element are identical. So as we talked about earlier, again, the presence of something like isotopes, where we have the same element, but they have different masses, sort of disproves that part of it. A given compound always has the same relative number and types of atoms. And again, that is true. Sort of that same proportion or ratio always comes about. And atoms are indestructible, again, you know, through say something like nuclear reactions and stuff like that. You really can sort of destroy and stuff like that. So in terms of what are still true out of those main parts, 1 and 3 on this question obviously would still be considered correct. Any questions on that there? Now, a couple of other laws, and again, we'll see a little bit more of these laws when we talk really about, gases. How do you spit that out? Gases. One is the Guy-Lussac's law, and he looked at really pressure and temperature relationships as the volumes of gases react with each other. And just a preview of it, again, we'll talk in more detail when we get to that chapter. But basically what he found was, as the pressure went up, so did the temperature. So there was that relationship, and vice versa. As the pressure went down, so did the temperature. And again, it's really talking about gas molecules. So as gas molecules are flying around, what causes pressure is the collisions that occur. So if we increase the temperature, we would expect them to fly around faster. The faster they fly around, we would expect a lot more collisions, and thus we would expect the pressure to increase. Vice versa there, if we are lowering the temperature, those guys are going to be flying around slower. It's going to take longer for collisions to occur. And because it takes longer for collisions to occur, we would expect the pressure to start to go down. Our good friend Avogadro also had sort of a hypothesis or a law, and one of them was that when we deal with gases at temperature and pressure, basically the volume of the gas is proportional, that's the little symbol there is, to the number of moles of the gas. So it's Avogadro, like Avogadro's number, so you expect moles to be involved. And again, we'll talk more about that, I think, in a later chapter here. So we'll kind of skip this for now. We'll see it later. All right, so again, this is sort of a picture of what Dalton sort of thought about in terms of how atoms come together. And again, this is an example that, as you can see, they really are, all of them really just a combination of two elements, nitrogen and oxygen. But depending on sort of the combination, like how it comes together, maybe who's in the center, who's in the outside atoms, you may get some different properties that occur. So, you can think about elements as, again, sort of as far back as you could go. Obviously, on the periodic table, it's all the elements that we see. But elements, are thought of, really like sort of the alphabet. So what do we got still? I think 26 letters. Maybe it's changed. Hopefully not. But maybe 26 letters is still what we got going on. But again, different combinations, obviously, of those letters gives us a whole dictionary. If you remember what a dictionary is, it's not Google. It's like a book. You used to look it up, words, before you Google things. But you get a whole dictionary of different words and different meanings that come from those words. And the same idea, obviously, in chemistry, there's only so many elements, but really sort of different combinations of these elements bring about different sort of compounds and perhaps molecules and different sort of properties associated with it. So based upon Dalton's sort of atomic theory, there is sort of a good idea about sort of what's happening in terms of the atom. It was basically defined as sort of the basic unit that can go into chemical combination. And there was a lot of sort of experiments that were done from 1850 to about the 20th century. And what they demonstrated was that even though really atoms are, really small sort of particles, they do contain sort of an internal structure of even smaller particles. And those are what are sometimes referred to as subatomic particles. And those subatomic particles, we're going to talk about each of them here in the future, and how they sort of came about. But we have electrons, which, as you may know, are negatively charged. We have protons, which are positively charged. And we have neutrons, which have no charge associated with it. So, sort of the discovery of a lot of these guys allowed us to sort of really have a good understanding of what is going on in terms of the structure of the atom. And really, a lot of early work in terms of the atom really revolved around kind of the electrons. So, a lot of that early work was done with the electrons, and it was done by sort of the development of what is sometimes referred to as the CRT. CRT stands for cathode ray tube. And perhaps you're familiar with a cathode ray tube. If you have seen an older TV that has sort of a big back on it, not like a flat screen or anything like that, or maybe an older computer monitor that kind of goes out in the back as well, those are usually CRT tubes. As we'll talk about in just a second, they sort of shoot a particle of negatively charged protons. I'm sorry, negatively charged electrons. And this sort of fluoresces and stuff like that. So we'll see a picture here in just a second. So the person that really started out with a lot of work using the CRT tube was J.J. Thomson. So Thomson did a lot of work. And as we talked about before, that basic principle, which is sometimes referred to as electrostatic attraction. And that is basically opposites attract. So again, positive and negative things are attracted to each other. Things with the same charge, two negative things, don't really want to be near each other. And two positive things don't really want to be near each other. So really the CRT tube really has sort of an electrical field, has like a negative side to it. It has a positive side to it. And when it's shooting this beam, they're kind of negatively charged electrons basically. So they're going to move away from the negative side and be attracted to the positive side here in the CRT tube. And what he was able to do with the CRT tube was he was able to determine what is referred to as the charge to mass ratio of an electron. So he was able to come up with what the charge to mass ratio of an electron by using the cathode ray tube to do so. And that's an important thing to know. Charge to mass of an electron discovered by Thomson using a CRT tube. So what does the CRT tube really look like other than my really bad drawing? It looks something like this. That's a much prettier picture, I'm assuming, than what I drew. Sort of looks like what I drew if you close your eyes, I suppose, tilt your head. But this is basically a CRT tube. And again, you see there's a negative side, there's a positive side, and this beam of electrons are basically moving in this direction towards the positive side. A lot of times what people will do is put some type of material here on the end that as those electrons sort of hit it, it will sort of fluoresce and sort of obviously give off some light and color as it gets hit by those sort of electrons that are moving. Again, if you're old enough to remember a TV like that, that's basically what your picture tube does or did. And they would oftentimes send people to, when they had TV repairmen, like estimate house calls, they would come out and kind of fix your picture tube by adjusting and stuff like that. So there's Thomson staring at his CRT tube, and he was able to come up with that charge to mass ratio of an electron, and that's actually the number right there is minus 1.76 times 10 to the 8. The C is a coulomb, and that's a unit of electrical charge, and G is a gram, so that's a gram. and that's basically a Coulomb, which is an electrical charge. So the charge per mass of an electron was found to be that number there. And that's a very good sort of first step in sort of understanding about electrons. And there were some experiments that happened sort of after Thomson. And the next really important experiment to know was the one that was really performed by Robert Millikan. And Robert Millikan performed what is sometimes referred to as the oil drop experiment. And it is pretty much what the name sort of implies. The oil drop experiment is he basically set up a container. And in that container, he had really an electrical field happening. He basically shot in there some oil droplets, kind of heated them up, atomized them. And, you know, when it had like a little hole there for it to go through. And normally what we would expect is obviously the drop would start to fall, right, by force of gravity. As it would go through the hole, it would go down and start to drop to the bottom. What Millikan was able to do was he was able to really adjust the electrical field in such a way that by adjusting this electrical field, he was basically able to make the drop of oil basically just kind of hang there. It wouldn't obviously fall, it wouldn't go up, it wouldn't go down. He was able to really sort of dial in on sort of the electrical current that's basically was needed to keep that oil droplet from falling. And really the main result that sort of came out of Millikan's oil drop experiment, and again, important to know the oil drop experiment, sort of what it was, and what it came out of it, which we'll talk about right now. What really came out of the oil drop experiment was he was able to basically figure out the charge on an electron. So Millikan was able to figure out the charge on an electron. Here's a much better picture than what I drew of his setup. Again, he would shoot the oil in. He's got that electrical field set up, a little spot where the oil droplets would come down. And again, he was able to really adjust it in such a way that it basically just hung there. And he was able to come up with the charge of an electron. And this is the charge of an electron minus 1.6 times 10 to the minus 19. Now, this was important because if you think about sort of the two experiments we just talked about, which was two things that you should know, which is Thomson using the CRT tube, he was able to basically figure out the charge to mass of an electron, Thomson. Millikan was able to figure out the charge of an electron. The importance of both of these experiments is if you took Millikan's discovery, if you will, and you divide it by Thomson's discovery, which is the charge to mass of an electron, the charge will cancel, and you're able to basically figure out what the mass of an electron is. So by putting basically both of those experiments together, they were able to really deduce sort of the mass of that subatomic particle, the electron, and that calculation is here. So again, if you take both of those numbers together and you do the calculation, you see that the mass of an electron is 9.09 times 10 to the minus 28 grams. And now we really have some good understanding about our atom and one of those subatomic particles, which is our electron, which again had our proton, neutron, our electron. We definitely know from these experiments it's negative. We also now know really what the mass of it is, which is 9.09 times 10 to the minus 28. Any questions on that? And again, if you do have questions, feel free. You could use your microphone, you could use the chat box, whatever you'd like to do. A reminder as well, when we look at a number like 9.09 times 10 to the minus 28, it's a fairly small number because minus 28 means we are moving like 28 places to the left and putting zeros in front of it. So obviously not a giant number in terms of the mass. So now that we sort of have our identification of one of the sort of important parts of the atom, we're going to now focus on some experiments that helped us understand maybe the other parts of the atom. So we're going to move to the proton and the nucleus next. And really, by the early 1900s, there was a couple of things about the atom which was sort of commonly clear or thought of, and that is that it definitely contained electrons, as we just saw from those experiments. So it definitely has those electrons happening. But the atom itself is thought to have been electrically neutral. So clearly, if we have some particles in the atom that are negatively charged, and if the atom is neutral, the only way to do that is we do need to have something there that is positive in terms of charge. So we need some type of positive to balance out that negative charge that we know is there from those electrons. And sort of the earlier accepted model of the atom is one that's referred to as the plum pudding model. And you do need to know this model, and that Thomson came up with it. He basically thought that the atom was sort of this sphere, and kind of spread out in this sphere was all the positive charge, sort of spread out all over. This is all the positive charge, kind of really spread out and all over this sphere. And what he thought was what was sort of embedded inside was these negative electrons were embedded inside. It's called plum pudding because that's a dessert. And the dessert has basically pudding and raisins. And he thought the raisins were like the electrons. And obviously the pudding was the positive charge sort of spread out all over. Now, the other important part of his sort of theory here of the early model of the atom was, in addition to having this positive charge spread all the way out, all these negative electrons embedded inside, he felt that most of the mass of the atom was those electrons. So he felt that we have this positive charge spread out, we have these electrons embedded inside. I feel like most of the mass of the atom is going to be made up of those negatively charged electrons. And this was sort of a really accepted model of the atom. And again, you should be familiar with what this model of the atom looks like. Here's a much prettier picture than when I scribbled on the page there. And again, you can see the blue is sort of this sphere of positive charge that's sort of spread out all over the atom. We have all those kind of pink or red circles in there, which is our electrons that's embedded inside. And again, his idea was that most of the mass of that atom was the electrons. So this was a very good sort of thought about the atom, a nice little sort of model of the atom. And much like other things, sometimes things do get maybe disproven. And a super important experiment, not like the other ones weren't super important, I'll just use that word super here today, was one that was done by Rutherford and some other guys like Geiger, who you might be familiar with, Geiger counter radioactivity. They did what is known as the gold foil experiment. And pretty much like the name implies, they basically took pieces of gold foil and other metals, and they shot what are known as alpha particles at them. So what are alpha particles? Alpha particles have this sort of symbol. They are positively charged radioactive particles. They're basically, for the most part, helium. They're like the helium nucleus. There's also other types of radioactive particles like beta particles. Beta particles are negatively charged, almost like an electron. And they also have gamma rays, which perhaps you remember as well, and we'll see it in a later chapter. Gamma rays have no charge. They're really just pure energy. They're very, very high in energy. So he used these sort of particles, and he really used alpha particles to really sort of shoot at atoms and really try to make sure, hey, is this really the sort of structure that is there in the atom? Now, one important thing, as we talked about in terms of opposites attract, is the idea that, if you had something, let's say like an electrical field or something like that, and you shot a particle and the particle sort of bent towards the positive field, we would know that that particle is probably negatively charged, right? Because opposites attract, so negative, positive, going to kind of go upwards. If we shot a particle and it sort of bent down towards the negative part, we would expect that particle to probably be more positive. Again, the positive and would go towards the negative side. And if we shot a particle and it just kind of sailed straight, didn't bend or anything like that, we can make a pretty good assumption that that particle is probably something that does not have a charge. So by these sort of particles having charges, we could really take advantage of that and try to discover, what is going on with the atom a little bit more. So if we think about sort of the early model of the atom and sort of what Rutherford was going on, which was this picture back here, which was our plum pudding model, he felt that when he did shoot these alpha particles, right, which are these positively charged particles, and if he shot it at an atom that had this sort of setup, has all that positive charge that's really spread out, these alpha particles are heavy, they're moving really fast. So you would expect sort of the alpha particles to go through with probably a little bit of deflection as they go through. So sometimes, for example, if you think about like, if you took like a brand new, just like one piece of paper, single piece of paper, just had it spread out, and you like held it on both sides really tight, and you took like a pen or something and you shot it at the paper, right? It probably would hit the paper and go through the paper, right? But a little bit of deflection as it went through, right? It would be able to do that. But if you took that same paper and you kind of folded it, that pen is not going to go through. So when he did this experiment, it was set up like this here. Again, we have a source of alpha particles shooting at these pieces of gold foil, which is essentially the atoms. And again, based on what he thought was going to happen was, hey, that thing is going to go through, maybe a little bit of deflection. And what he actually saw was kind of surprising. He saw that most of the alpha particles went right through and just kind of hit the detector straight on through. But what they did recognize and saw was that every so often, these alpha particles would be scattered at these really large angles. They would even come back this way as to sort of where they were shot at certain points. And that was very surprising based on really the early model of the atom. So, if we think about the ones that just sailed through with no problem, that means that they had to hit something that was nothing, basically, right? Otherwise, they would have went one way or the other. But pretty much because they sailed through with really no deflection, there's really nothing in his way, sort of empty space, right? But how do we explain sort of those guys that came in and hit something and bounced off at these really large angles, maybe even came back to where it came from? What we know is it had to then hit something that was very, very positive in terms of its charge, right? These alpha particles are positive. So in order to be deflected at those really big angles, because things with the same charge definitely don't want to be near each other, it definitely had to hit something that was very, very positively charged. And that was sort of what I was saying just a second ago. Again, we talked about if you took sort of the paper and it was really stretched out, all that positive charge really all over the place. Again, if you shot sort of the pen at it, it would pop through the paper probably, maybe with a little bit of deflection. But if you took that paper and all that positive charge and folded it and then kept folding it on each other, where they say you could only fold a piece of paper like 6 or 7 times, right, before you can't do it anymore. And you got this piece of paper that's like this big, and you shot or try to throw a pen through it. It's definitely not going to go through it. It's going to bounce off, right, because it's really very densely positively charged. It's not going to let that pen go through. And what they found as a result of this experiment was sort of surprising to them. They definitely found that, these particles, most of them went through undeflected, which again meant they pretty much didn't hit anything. But we did have these particles that really did bounce off at these really large angles, which meant that they had to hit something that was very, very densely positive, because those alpha particles are positive. So positive hitting positive, going to make them bounce off at these really large angles. Sort of like they described it as like shooting a gun at a piece of paper and having the bullet come back. Those are things you don't sort of expect to happen. So what that meant was they almost had to go back and go, well, I'm not quite sure this is the correct model of the atom anymore. And through his experiments, which is why it's a really important experiment, the gold foil experiment, basically sort of disproved the plum pudding model of the atom, which was sort of the early model of the atom. So they had to sort of reimagine what the atom was as a result of their experiment. And basically, for the most part, the atom is sort of what we see imagined here on the right. It's basically mostly empty space. And as we will see, that is essentially why when they shot most of those particles, they didn't have a problem. They kind of sailed right through and nothing really happened. They also felt that it had to contain this very positive, dense core, which was later referred to as the nucleus. And as we'll talk about here in just a second, inside the nucleus, that is where we find our protons, which are positively charged. And what they thought about was that the electrons are out from the nucleus, not embedded inside, and basically moving around the atom in a really non-orbital type way. So it's not moving in pretty circles or anything like that. So his explanation, as I just mentioned, is really what we considered really what the atom is now, sort of the modern atom, the current version of the atom, if you will. And the other really important part was they found out that most of the mass of the atom was actually the nucleus and not the electrons. So the nucleus, which contained the protons at this point, later we'll find out that's where the neutrons are found as well, makes up most of the mass of the atom. And again, just a reminder, a couple of things. Again, our protons positively charged, later neutrons have no charge, and electrons are out from the atom. And as you may know, or maybe don't know, just so you know, they really don't move in pretty circles. They move pretty randomly about the atom. So, sometimes people think about electrons, maybe biology, sometimes they teach it as well, that the electrons are traveling these pretty little circles. And as we'll talk about in a later chapter, next chapter, I think as well, for sure, they actually don't travel that way. So electrons do travel in a fairly random pattern around the nucleus. Now, is there attraction between the electrons and the nucleus? And the answer you should have is yes, there is an attraction between the electrons and the nucleus. And that's because electrons, again, are negatively charged. The nucleus is positively charged. So there is that opposites attract, so that negative positive attraction. And as we'll talk about in later chapters, that's why certain electrons are involved in bonding, ones that are further away from the nucleus. And there's certain electrons that are not involved in bonding. Those are the ones that are closer to the nucleus and held a lot tighter. Any question on Rutherford? So in terms of Rutherford, you need to know the gold foil experiment. You know what it is. You need to know what he thought, obviously, the atom was going in, which was the plum pudding. You need to know what happened and what was the result of it, which is essentially no more plum pudding. And obviously the new version, I guess from 1911, newish version of the atom, or the current model of the atom, which again is our nucleus that has protons in the middle, as we'll see in a sec, and also our neutrons and electrons traveling at some surface. Most of it is empty space, and most of the mass of the atom is a nucleus. Any questions on any of that? This is just a table of some of the experiments and sort of the results that came about that we talked about. So just for review, you can kind of go through that. It kind of summarizes, really a lot of the early and main experiments that were done that led us to sort of understanding the nature of the atom. So let's talk about protons. That was obviously discovered in the nucleus. And through experiments, it was found that the mass of a proton is 1.67252. We'll see why it goes out to so many places in just a second. Times 10 to the minus 24 grams. And just a reminder that the electron that we saw earlier had a mass of 9.09 times 10 to the minus 28 grams. And in comparison of these two, the proton is about, as it says, 1,840 times heavier than any electron that's flying around. This is also why it sort of validates Rutherford's idea that it is the nucleus, where protons are, that makes up most of the mass of the atom. So since those protons are in there, and again, as we'll talk about here in just a second, and our neutrons, and it's heavier than any electron flying around, it does make sense that most of the mass of that atom is made up of, again, that nucleus. At this sort of stage of the game, a couple of things about sort of the atom. Again, the nucleus is most of the mass, but it's a very small sort of volume. So like usually a football stadium, like on the 50-yard line is like a marble or something like that. That's sort of the idea of the nucleus relationship. If you ever been to the Superdome, I have. Very scary seats. You ever sit in the seats at Superdome, you feel like I'm gonna fall off sitting down. So it's a good, nice place, but very scary sometimes. Just the seats, the way they're angled. Protons, again, are confined to the nucleus. And again, those electrons are basically moving around the nucleus in these sort of non-circular patterns, so random patterns, as we'll talk about, I think, in the next chapter. Again, you really won't know in terms of electron at any given point exactly where an electron is or how it got there or how it's traveling. And really, the more you know about sort of where it is, the less you know about how it's moving, and vice versa. So again, keep that in mind, because a lot of times people come in with that sort of orbital idea of electrons, that they're traveling these nice, pretty circles, around the nucleus. So that leaves us to sort of, there was always this idea after Rutherford and so forth that in addition to protons, in addition to electrons, that there really was some other subatomic particle that was present. And really in 1932 by Chadwick, he did a lot of experiments, sort of like with X-rays, and he did sort of discover the sort of third subatomic particle, which is the neutron. It has a mass of 1.67495. And the reason why the neutron goes out that far is, as we just saw, the proton was something like 1.67252 times 10 to the minus 24 grams. What that means, in comparison to our electron of 9.09 times 10 to the minus 28 grams, in comparison of our three subatomic particles, it is actually just barely right about there that it is the neutron that is actually the heaviest. So the neutron is the heaviest, followed by the proton, which is pretty close, followed way down the road there by the electron. So the neutron is also about 1,800 times heavier than any electron. So that even further allows us to understand that, like Rutherford said, because protons and neutrons, they are both found in the nucleus of an atom, and both of them individually is about 1,800 times or so heavier than any electron that is basically flying around. That again does make us understand that pretty much the most of the mass of the atom is made up of that nucleus. Any questions on that? And this table, again, just summarizes the masses that we just talked about of those three subatomic particles. Do you need to know the numbers of the masses of each of the subatomic particles? The answer is no, you don't. But you do need to know, that the neutron is the heaviest, followed by the proton, and the electron is the lightest out of all of them. Obviously, you also need to know the charges that we talked about, electrons being negatively charged, found outside of the nucleus, flying around in a random behavior, protons found inside the nucleus, positively charged, and neutrons also found inside the nucleus, and then they have, again, no charge. And as we talked about as well, just to kind of finish up here about atoms, again, the nucleus, as we talked about, is very small compared to the overall size of the atom. Again, a lot of the atom is filled with that sort of empty space. In that empty space is essentially where we find sort of our electrons flying around, sometimes referred to as sort of the electron cloud, where we see those electrons moving sort of back and forth. And again, here's sort of a visual picture of what we've been talking about. This is, again, sort of our current model of the atom, the accepted sort of model of the atom. Again, you can see that very small part in the center. And this picture is our nucleus, where we have protons and neutrons. And obviously all that sort of pink color or red color is what's sometimes referred to as the electron cloud or electron density. And if you, not sure how well it picks up, but if you look in sort of this area here, it's a little darker pink than as we sort of fade out this way. It kind of gets lighter and lighter and not so much pink. And usually areas where it's really dark in terms of, say, that pink color, basically means that's a very good probability of finding electrons in that area. There's a high probability. Not sure where they are or how they're moving, but there's a good chance of finding them. And as you sort of feather out towards the edges there, where it kind of goes to light pink and kind of no pink, you probably have a much lower probability of finding an electron. And again, that has a lot to do with that attractive force. Again, electrons closest to the nucleus, because the nucleus is positively charged overall, electrons are negatively charged. It's going to be a lot of strong attraction that's happening. But at some point, even if you have electrons, there's a lot of electrons in the way. So it can't really get in and be attracted as much. And again, there's less probability of finding electrons further out. And as we talked about before, those electrons, again, are sort of traveling randomly about in this particular area. Any questions on the experiments that led to our understanding of the atom, what you need to know? Any questions on anything we talked about here today? Okay, so we'll wrap it up for lecture here, I think.